Welcome. In this video, we're going to check out some examples of taking things in open form and putting them into closed form. So in this first example, if we take a look at what we have a series, that's a bunch of terms that are being added together. And the first term has a 1 and an n, and if we look, then the 1 increases to 2, 3, and then so far all the way up to n minus 1 and n. And the other part of the term, the right-hand side part, goes downhill, n minus 1, n minus 2, all the way down to 1. So let's take what we have and try to write a sub n in summation notation. So our summation notation will have n different terms, so we'll write I equal 1 going all the way up to n, and each term has an I that multiplies, and each term has the other part that goes downhill, the n minus 1, and so on. So we'll multiply the I by something, and what we want to multiply it by would be n at first. So if we write down n, then we would want to keep subtracting away from n. So we'd first subtract 1, but this would put us at n minus 1 for the first time we plug in I equal to 1. So let's write plus 1. And now we have a sub n properly represented. Okay, so on our next step, let's try to separate the i's and the n's. So the summation be I equal 1 to n, and we can multiply the I into the bracket. So we have I multiplied by n plus 1 minus I squared. So we have the sum of all of this stuff here. Now, in a previous video, we discussed what happens with the sum of consecutive integers from 1 to n and the sum of consecutive squares from 1 to n. So we can go ahead and use the fruits of our labor here, and instead of writing I, we can write s sub 1. All of those terms are being multiplied by n plus 1. And instead of writing I squared, we can write s sub 2. So if we think back to our previous video, s sub 1 was n plus 1, so we could write n multiplied by n plus 1 squared, and then divided by 2. And s sub 2, that was n multiplied by n plus 1 multiplied by 2n plus 1, all divided by 6. So now we have a beautiful looking closed form of this possibly more ugly form that we started out with. At least this form down here is straightforward to calculate. It doesn't matter how big n is. You can just plug it in, and there's only so many operations that we have to do there. But as n gets bigger and bigger and bigger, because of the dot dot dot, we have to do more and more operations. That gives us the advantage of a closed form versus an open form. Okay, let's take a look at the next example. Okay, so here we have a series. This time in the series, the power is the thing that's growing. So this is what we call a geometric series, and we're going to try to find a closed form for this. So the strategy that we're going to use is call this closed form S that we're searching for, or the sum that we're searching for, and take S and multiply it by x. So xs. So what that would do is make x to the power 0, x to the power 1, plus x to the power 2, plus dot dot dot, then x to the power n, and there would be one more term, x to the power n plus 1. Now to find my closed form, I'm going to take those two expressions and subtract. So top expression minus bottom expression gives me s minus x multiplied by s. And then all of these terms in the middle here, they all cancel out for us, even the dot 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 all the way up to the x to the power n. So all that's left is x to the power 0 minus x to the power n plus 1. So on the left-hand side, we can go ahead and factor out an s. So we can write s multiplied by 1 minus x. Our objective here is to solve for s. So we can divide both sides of this equation right here and right here by 1 minus x. So s is equal to x to the power 0. How about we write that as 1 minus x to the power n plus 1 divided by 1 minus x. Now sometimes people prefer to present this closed form by multiplying the top and bottom by -1. So that could be an option. Possibly people think maybe we're going to be plugging in a value like 2 here or 5, and then rather than dealing with negative numbers, let's do x minus 1 instead of 1 minus x. And of course that's just kind of a matter of taste. But we'll do it here to present our final answer. So multiplying the top by -1, we get x to the power n plus 1 minus 1, and the bottom will be x minus 1. Now here's our nice fancy closed form, a solution to a geometric sequence that has a base of x. Now there are two values, there are two real numbers that x cannot equal. Can you think of those two numbers? Maybe pause the video now and think of which two real numbers we cannot have plugged into this formula. Okay, so those two numbers are, well, for one, we divided both sides by 1 minus x, so we can't have x equal to 1. And the other number that we cannot have x equal to is 0. If you look at this expression right here, you have x to the power 0. If you take 0 to the power 0, that's an undefined expression. So we also don't want to plug 0 into that formula. Every other real number is perfectly fine. Now you might say, well, it's not even really very much of a worry about 0, because if you're just taking powers of 0, forget the x to the power 0, but if you're taking other powers of 0, you'll just get 0 anyway. And if you're taking powers of 1, you're just going to get 1, and you're going to add the number 1 a bunch of times. So these special cases are not all that interesting. Okay, let's take a peek at our next example. Okay, so in our next example, we're going to be looking at combinations. So a combination is this type of thing here. We read this as n choose k. So it considers the number of ways of choosing k objects from a group of n objects. I always like to draw a little picture down when I kind of think of this. So here's my grouping, and in that group, I'm going to say there's n objects. These objects could be whatever you like them to be. They could be maybe cards in the game of Pandemic. In the game of Pandemic, there is 7 cards, and you might say, well, I'm playing with my roommate or my wife, and I want to know all the different ways of choosing 2 of those cards. So if you do that, you would do 7, choose 2, and it would pick all the different ways, and you'd get 21 out of the deal. So a very important formula that comes up with combinations, possibly the most commonly presented formula, is Pascal's formula. So with Pascal's formula, it tells us that if we have n choose k, it's the same as these two combinations. So let's think about those two combinations. It's saying that, well, if you take 1 less and pick all the ways that you were considering with k, but 1 less, that's part of it. And then if you take 1 less and then choose all k of them. So the way that you can prove this is, let's say that you just pick one of your elements or one of your objects. Let's just say this object, and we'll just call it, a special one there. We'll call it star. So if we decide we're going to pick star in our group of k, let's say we're forcing ourselves to pick up star, how many more choices with n choose k do we have? If we're supposed to pick up k of the objects, and we say we must pick up the star. So if we pick star, so picking star says that there are n minus 1 objects left, and out of those n minus 1 objects, we're going to pick k minus 1 of those objects. And the other way that you could go about this is say, well, no, wait, I'm going to refuse to pick star. That would be the other option. So do not pick star. So if you say, we're going to refuse to pick up this one, then out of your n objects, you would still pick up k of them from the rest of them, but the rest of them are only n minus 1. So out of the n minus 1, you would now choose k. So these are the two different cases that exactly produce Pascal's formula for us, which is sitting right here. So that's our proof of Pascal's formula. So we're going to use this formula below to find a closed form for the expression that's sitting in front of us. So if we have I choose 3, and we're going to add up a whole bunch of choose 3s, what we'd like to do is maybe try to create some kind of cancellation so that it's not so complicated. Maybe we can get some of the combinations to cancel out with other ones. So the way that you can do this is move the n minus 1 choose k to the other side of the equation. So in doing that, we would get n minus 1 choose k minus 1, which will equal n choose k minus n minus 1 choose k. Now the reason why we're going to manipulate it like this is because these choose k's on the right hand side have a chance of cancelling out. There's going to be some positive ones and there's going to be some negative ones, and they're all choosing k. So let's plug that in to our summation and see what we get. So this summation from I equal to 3 going all the way up to n minus 1. Now instead of writing I choose 3, we're going to replace it with this side of Pascal's formula or Pascal's manipulated formula. And don't even really need to kind of think about, well, what's n and what's k? Maybe just think about up or down. So on the top, let's think about the top first. And let's just write in our two combinations. So one combination minus the other. And again, we're going to think about the top. So the I is there, and we're going to write something there and write something there. So reading across the top, it's n minus 1. So it goes up 1. And then the other thing on the top stays the same. So it's I plus 1 because it went up 1. And then the other thing on the top stays the same. So it's I. Now let's do the bottom. So the bottom, the transition from the left-hand side to the right-hand side, it's k minus 1, and then it goes up 1, and then up 1 again. So it's 3 here, so that means that it should be 4 right there. So we've changed a summation of choose 3s into some choose 4s. Let's write out these combinations now in a more expanded form. So down on my page, I want to write out, how about all of the positive combinations first? So if I plug in 3, I would get 4 choose 4. And then if I plug in 4, I would get 5 choose 4. And then plus on and on and on. Finally, I would plug in n minus 1, and I would get n choose 4. Now let's do the negative terms. So the first negative term, we'd plug in 3. So we would get minus 3 choose 4. And then we plug in 4 for I, and we would get minus 4 choose 4. And then we would plug in 5, and we would get minus 5 choose 4. And then minus ... all the way along. And then eventually we would plug in n minus 1, and we would get minus n minus 1 choose 4. So if we notice in this expanded version of our summation, there's a lot of cancellation going on. Notice the 4 choose 4 cancels out with the 4 choose 4. 5 choose 4s cancel out. All the way along, all the negative ones cancel out with the positive ones, all the way up to n minus 1 choose 4. So when this magic happens in a series, we call this a telescoping sum. Each term in our sum provides something to cancel out with the previous term. So what we're left with is just these two terms here that didn't cancel out, n choose 4 and 3 choose 4. Now 3 choose 4 might seem like a little bit weird. You have 3 objects and you want to choose all the ways of taking 4 of those objects, but there's only 3 of them to begin with. So this isn't undefined, it actually is defined. It's just defined as 0. So we say that there is 0 ways of taking 4 objects from 3 objects. So it's different from saying like something like divide by 0 or 0 to the power 0. Those things are undefined. 3 choose 4 is defined. It's just defined as 0. So all of this boils down to n choose 4. So that is our ending closed form. We've taken a bunch of choose 3s and changed it into just one choose 4. I always think that this formula is kind of neat. A whole bunch of choose 3s gives you a choose 4. You could do the same thing. There's nothing special about the 3. You could say a whole bunch of choose 4s added together would boil down to just a choose 5, and so on and so on. All right, next example. So we are going to show that this sequence is always an integer. And it's not so clear why it's always an integer. So we have a combination. Every combination is always an integer. You have objects and you're picking all the ways of getting those objects. You don't have any fractions there. But then we're taking that amount and we're saying we're going to divide it by n plus 1. So why should that be an integer? It's not so clear. We're going to play around with the formula for how to calculate a combination to help us out with this particular example. So a sub n is equal to 1 divided by n plus 1. Now above on our page we gave a formula for how to calculate combinations. We haven't quite played around with this one yet. So here's our formula. So we can take the number on the top and take the factorial, and the number on the bottom and take the factorial, and then take the difference of the two numbers factorial. That's how you can calculate what this number is. So we're going to use that below. So the number on the top, factorial, which is 2n factorial, and then the number on the bottom, which is n, so n factorial, and then the difference of the two numbers, 2n minus n, is just n, so n factorial as well. So what we end up with is 2n factorial on the top, and then on the bottom, n plus 1 factorial multiplied by n factorial. Now the idea here to try to show that this is an integer is to notice that, well, this expression here is very close to a combination. If the factorials on the bottom just had numbers that would add together to give me 2n, then I would have a combination right here. So the idea is to multiply this by something that will reveal a combination. So I'm going to multiply by n plus 1, Because if I multiply by n plus 1, there's an n plus 1 here and an n plus 1 there that will go away. Now, of course, we can't just multiply by n plus 1 for free. We have to pay the price and also subtract n. So now what's inside of the brackets here is exactly 1. So we've just multiplied by 1, and this is a legal move. What's in green here, there's no change in the equality. It's still equal to a sub n, as it was to begin with. So once we expand this out, so we're going to take the number that we have right here, we're going to view that all as one number, and multiply it by n plus 1, and the other part of the distribution, we're going to multiply it by n. So what do we get out of the deal? We get 2n factorial on the top, and then n plus 1 canceling out on the top and bottom, so n factorial, and then copy the n factorial, and then minus, there will be a 2n factorial on the top, multiplied by n, and then on the bottom, we have n plus 1 factorial and n factorial. So now if we look at the n here and the n factorial, we can get a cancellation there as well. N and n appear on both the top and the bottom. So let's go ahead and cancel those out. So we would get 2n factorial and n factorial, just copying from above, and then the other term becomes 2n factorial on the top, and n plus 1 factorial, and n minus 1 factorial. So now we have exactly what we were looking for. We cooked this up so that we'd get a combination here because we wanted to make sure we get rid of that n plus 1. So we have a combination here. We can verify that we have a combination because n plus n is equal to 2n, and these are all factorials. So this is a combination. And the same thing over here. This is a combination. You have n plus 1 and n minus 1. If you add those two numbers together, you get exactly what's in the factorial on the top, which is 2n. n plus 1 plus n minus 1 is 2n. So the two combinations that are here are 2n, choose n, minus 2n, choose n plus 1. So because this is an integer and this is an integer, and we're taking the difference of those two integers, we have an integer in the end. So the most common symbol that mathematicians use to describe integers is this funny, bold-faced Z symbol. So do you know what sequence of numbers these are? They are a very famous sequence, probably the most famous, maybe the queen of all sequences is the Fibonacci sequence. This is not the Fibonacci sequence. I would say that this is the second most popular sequence of all sequences. If you want to do a little treasure hunt, maybe you can pause the video now and check Google to see if you can find out what sequence of numbers these are. But I'll give you the answer now. These are the Catalan numbers. So if the Fibonacci numbers are the queen of all sequences, maybe the Catalan numbers are the princess of all sequences. Those two sequences solve so many problems. So thanks so much for listening. We'll see you on the next one.